right. Hello, everyone. Thanks for joining us. So for those who are new to this call, so we are here as part of Cohere Labs Open Science Community ML in Healthcare program. So our group regularly focuses on medical image analysis, clinical NLP, responsible AI, and we are fundamentally an open and a flexible community. We are always eager to explore new research methodologies, challenging topics that push us the boundaries of ML in healthcare. So if you have an idea or probably an area of interest, we encourage you to propose it and join our Discord channel. So without further ado, today we have Fatemeh, who's joining us for our guest speaker session series, who is currently working as a senior applied scientist at Microsoft AI, focusing on multimodal learning and data-centric AI for search and recommendation. She recently received her PhD in computer science from University of Washington, where her research centered on multimodal AI for digital pathology. Today, she'll be talking about one of her works on multimodal pathology and diagnostic AI. Fatemeh, the floor is yours.
Hi, everyone. Thanks for the introduction, Lima. I'm excited to be here and talk about some of my recent work on applications of AI in digital histopathology. Today, I will talk about a series of projects done while I was a PhD student at the University of Washington, from generating large-scale multimodal data to developing diagnostic systems for the field. So over the past few years, we've seen a major shift in pathology from glasses slides being reviewed under a microscope to high-resolution whole-side images on a computer screen, like the one that you can see here. And with this rapid growth of digital pathology, thousands of new cases are being scanned every day, and the diagnostic workflows are evolving to take advantage of this new data. But with this transformation also comes increasing complexity in how we navigate these massive images, interpret findings, and also maintain consistency across pathologists and institutions. As the number of pathology cases are increasing, the pressure on diagnostic systems also increases. This raises an important question. What do we actually need here to keep up with this demand? Well, first of all, we need improved accuracy and efficiency. Even a small improvements here can have a significant impact on patient outcomes. We need to have scalable systems with this increasing number of cases so that the systems don't slow down or break down. We need consistency because different pathologists may interpret the same slides differently, and this variability may become a real challenge at a scale. We also need support for rare cases, and we need cost-effective solutions so we can adapt widely. But all of this together, in order to achieve these goals, there are a few issues. First of all, there is a significant supply-demand issue in histopathology. Only 3% of NHS histopathology departments have enough staff to meet this clinical demand. And training pathologists is a long process. We cannot train pathologists fast enough. In the United States, it takes over a decade to train a well-versed pathologist. And even if we wanted to put resources into training pathologists, these diagnostic processes are very complex and time-consuming. So this raises the question, what can we do here? If we look at today's diagnostic workflows, a lot of the burden falls directly on the pathologist. They receive a whole slide image. They have to manually scan through these images, identify structures and patterns, and then translate everything into a diagnosis or prognosis. And this process is incredibly skilled, and it's slow, manual, and cognitively heavy. So the natural question here is that, can we use AI to help us with this process? The short answer is yes. It depends on how we design these systems. Traditionally, ML pipelines can look something, as you can see in the green box here, where we can have pathologists annotate these images, or nowadays we can have computer-aided systems to help with this annotation part. And then they perform pre-processing steps, and then we can use machine learning approaches to perform that diagnostic or prognosis task for us. But with the current state of these systems, they can only perform as a support or assistant to pathologists. We cannot replace pathologists with these systems yet. But why is that? Because existing AI models function as black boxes. It makes this decision-making, like without offering interpretable explanations, it makes it hard for pathologists to actually trust in these systems so that they can adapt in their clinical workflows. And also, these AI models analyze whole site image at patch level, or they use multiple instance learning approaches, which lacks that holistical reasoning of human pathologists. How can we bridge this gap? How we can generate AI systems that can mimic pathologists' viewing behaviors or clinical practices and diagnostic decision-making? There are a few challenges in the way of reaching that goal. First of all is that in the histopathology domain or the medical domain in general, we have this scarcity of large-scale data, which we don't have in natural domain. And it limits us in developing multimodal models that are capable of understanding both visual and textual information. And finally, we need ways to integrate these models into complex frameworks so that we can automate the entire diagnostic workflow. So that's why our group started working on a series of projects to address these issues. I will get into the details later, but Quilt-LLaVA is the largest data set in histopathology that we developed. We use that to train Quilt-LLaVA, a VLM for histopathology, and finally PathFinder, our latest work, which is an agentic system to mimic the diagnostic workflow. But let's just start with the data part. Where can we get this data from? So in the natural domain, data sets like the Lion 5B that are taken from internet have shown that we can train good foundation models in that domain, but we lack that in histopathology. And all of the traditional existing sources that already have been used, like Twitter or PubMed, they are scarce. We don't have enough medical content there. So that's where our group realized that there are a lot of educational medical content on YouTube that we can use and extract aligned image text pairs from. If you remember the video that I showed earlier today, it was actually taken from YouTube. It's the same video that you can see here. We don't have audio, but if we had, you would hear the pathologist going over this case, zooming in and out, navigating, using their mouse cursors to point to specific regions and describing them in natural language. So it is a very rich resource for us to extract aligned image text pairs. We introduced Quilt pipeline to extract this data. It includes several modules that I will briefly go over each one. First, we need to identify those videos. We use YouTube's API to search using 500 keywords across 18 subpathology fields, which resulted in 287 channels. So among those channels, we had about 64K videos, but we're not interested in every video. For example, videos that have slideshows or have a static histopathology images are not of interest to us. We are interested in types of videos. We call them a narrative style video, where we have consecutive histopathology content over time and narration of the presenter in that video. And the way we filter for those is that we take the first few seconds of each video, we check for consecutive frames. We have trained in-house classified histopathology classifiers that can tell us whether it's a histopathology image or not. And once we confirm that, we check the audio. If we have English audio consecutively over those frames, then we flag them as a narrative style video. Currently, it's limited to the English content only, but there is room to expand that to other languages as well. So this results in about 4,000 videos, about more than 1,000 hours of histopathology content that we use to extract our data from. So we're interested in two modalities, image and text. For the image, as I mentioned, we have histopathology classifiers where we can extract histopathology content, and we perform some denoising, like we deduplicate and remove the blurry images to have a clean data set. On the text side, we're working with a speech at the beginning, and we use ASR models to go from speech to text. And from this point forward, we're working with text only. But this text has noise because these ASR models, sometimes they have difficulty in identifying the technical keywords or phrases. And also, people have different accents, so we have some noise that we need to fix. We use LLMs and UMLS entities to perform this text correction, and we also prompt LLMs. At the time that we were working on this, we had access to GPT 3.5. That's what we use here. We prompted it to extract the medical relevant information and also the subpathology category of that case for us. And this is because these videos are usually in a conversational format. You can think of it as a Zoom call that multiple people are on it and they are discussing a case. So the presenter can pose a question, the audience engages, and this goes back and forth. They use filler words. So we wanted to denoise this and only keep the medical relevant information. That's why we prompted LLMs to extract that information for us. And once we have that, we can pair these two modalities based on the time of them happening. And with that, we have our data set, which includes the images, the medically relevant text, the subpathology, and also we had trained a magnification classifier where it can tell us whether the image is at 0 to 10x, 10 to 20x, or higher than 20x magnification level. We use that data and we got a clip architecture to train a model called Quilt-LLaVA, where if you're familiar with clip architecture, we have a text encoder and image encoder, and with a contrastive learning approach, we try to learn a shared embedding of image and text, which we can later use for downstream tasks like image text retrieval or classification. Here I will just show our benchmark on zero-shot classification. We evaluated our model on 12 different public data sets, and we compared against the original clip without any fine-tuning. Biomed Clip, which was a clip model developed by Microsoft Health Futures team. It is trained on the entire biomedical data, not just histopathology, and the data is taken from PubMed articles. And then PLIP was another model. It is histopathology specific, but the data is much smaller. It's taken from Twitter posts. So in most cases, except these two, we were outperforming state-of-the-art models. But for further experiments and evaluations, you can refer to the Quilt-1M paper. But the next building block towards an end-to-end diagnostic framework was a VLM. That's where the Quilt-LLaVA model comes in. So VLMs in the natural domain had shown great potential. An example was LLaVA. We're using a good instruction tuning data set. They were able to train a good VLM that can perform the visual question and answering task for us. They use the COCO data set, which has image and text pairs, and it also has bounding boxes of the objects that are present in these images. So they use this data set to generate instruction tuning data. Basically, it's question and answers, and they train a model for this. Following the success of LLaVA in the general domain, the medical community also wanted to follow and have their version of LLaVA. So they used the LLaVA architecture, train it in 2 stages to get LLaVAMed. This was also one of the first instances developed by Microsoft, which can perform medical VQA. But these models, the existing models at the time, had limitations because they were trained on image text pairs taken from PubMed articles. But these PubMed articles, they lack visual grounding. So unlike the COCO dataset where we had the bounding box information, for these cases, we don't know where in this image this text is describing. So we lack that. We lack that the spatial understanding in these images. And also these are isolated image patches, meaning that we don't have the reference whole site image. We are lacking that holistic whole site image understanding. So that's where we wanted to use the data that we got from YouTube, which is we also have like mouse cursor pointers. We were thinking maybe we can use that mouse cursor pointers to actually ground the narrations, speech or text to the visual areas. We came up with this pipeline to perform that task. You can think of a video that goes through the entire case. We divided into multiple stable chunks. Each stable chunk is actually a short clip, like a 20-second video out of the entire video, where the background is stable. It means that the pathologist has fixated on a specific region, and they're viewing it, they're using their mouse cursors to point to specific regions and describing them. So the background is not changing. So within each stable chunk, we calculate the median in pixel space. Basically, this is our background, our static background, and we subtract that from every frame. So what we're left with is the pixels that are referring to the mouse cursor location. And after applying some thresholding, we will extract the coordinates of those cursors, and then we can see which regions they were looking at. We have those locations here. You can see color-coded based on time. They start from talking about here and then move forward to the blue regions. So while the narrators or presenters are describing different concepts, they may start talking about a specific region and then move to another part. So these different concepts that they're describing, they are far away spatially and also temporally. So we apply some spatial temporal clustering here to extract concepts or regions that they're describing. For example, in this case, we have two bounding boxes, and we also found the largest bounding box that includes all of those mouse cursors. And then we can map this to based on the time, we can map this to the image description. So for example, the first part is referring to the screen part, and then it ends with the blue part, which refers to this bounding box. And similar to the COCO dataset and how LLaVA was formulated, we append the bounding box coordinates to the image description. So once we have that visual grounding, now we get to the training of Quilt-LLaVA. We use the similar pipeline to LLaVA-Med. We get the LLaVA architecture. It includes a vision encoder and NLP projection layer, in addition to a language model. So we pass the image through the image encoder and NLP projection to get the visual tokens. We get the language tokens on the language side as well. We concatenate everything and pass it through the language model and train it with an autoregressive approach. Then we want to train it in two stages. Stage one is pre-training for histopathology domain alignment, and stage two is fine-tuning or instruction tuning. Basically, we want to tell the model how to respond to specific question types. That's when we have Quilt-LLaVA, which can perform downstream tasks for us for act as a multimodal chatbot or answer visual questions. So for the first stage, we already have the right data set for it. We can use Quilt data, which it has like image text pairs, a large data set. We can use that to train it, but for the second stage, we need that instruction tuning data set. So we need to generate it. These are basically question and answers about these images. So for this instruction tuning dataset, we developed two different sets of prompts. The first one are independent prompts, which were already used in the literature, conversation-based and detailed description-based questions. So conversation-based questions are multiple back and forth question and answers between a user and an agent. So basically, we prompted GPT-4, we provided the description and bounding box information and asked it to generate multiple rounds of back and forth question and answers for us. And the detailed description is similar, but it only consists of one question and answer. We randomly select a question, asking it to describe the image in detail from a predefined list of questions. And then, as you can see here, the question, the answer to that question is longer and it has more details. The second set of prompts that we were actually proposing in this work are reasoning-based prompts. We wanted to distill that complex medical reasoning ability to our model. So we came up with these two: complex reasoning and iterative abductive reasoning. Basically, we want the model to think further than that one isolated patch or description and consider the entire whole slide image. So in order to do that, in addition to the description content, we wanted to have the diagnosis and also some supporting facts. Where we get this data from, if you remember, this images actually come from a YouTube video. So for that entire YouTube video that goes through an entire whole slide image, we can get the entire transcript, prompt GPT-4 to extract the diagnosis and supporting facts that the narrator is presenting in that session that supports that diagnosis for us. So in addition to this description, we provide these to the GPT and ask it to make a diagnosis based on this description and also this additional information about the whole site image. The last one, the iterative abductive reasoning one, you can think of it as a conversation between two GPT models. One is a student GPT and the other one is a teacher GPT. The student GPT has only access to this description part, but the teacher GPT has this additional information. So this starts with the student GPT describing this image, trying to reach a diagnosis and asking the question, and then the teacher GPT can correct it, provide some hints based on the further information that it has access to, and this goes multiple rounds until the student GPT reaches a correct diagnosis, or we reach the maximum iterations of questions and answers. So with that, we trained Quilt-LLaVA, we performed some evaluation. You can refer to the paper for that. But until now, we know that Quilt-LLaVA is capable of VQA. Sorry, is there a question? I don't see the screen.
Hello.
Hi.
If I may, would you please repeat what kind of information the student and the teacher have access to?
Sure. So the student has only access to this description part. So just to clarify, in all of these, we are not showing the image to GPT. We're only working with text. So all of these question and answers are generated based on the text only. I'm just showing the image as a reference here. But the student GPT has access to the description part and also the bounding box, which is appended to the description. And the teacher GPT has everything. It has the description, the diagnosis, and supporting facts. Does that make sense?
Thank you. Thank you very much. I appreciate it.
Yeah, sure. So yeah, as I was saying, Quilt-LLaVA is capable of VQA. You can refer to the paper for that. But the question is Quilt-LLaVA capable of a standalone diagnosis? Probably not, because histopathology diagnosis is a complex task. It is not just image classification, because it is multimodal in nature. Pathologists use both visual information and also textual information to reach a diagnosis. It is usually done over multiple iterations as they navigate these images, go through different regions multiple times. It is done at multi-scale. They can zoom in and out multiple times at different scales. They can zoom in up to 60 times to view at a cellular level granularity. And also it requires ROI localization. ROI stands for region of interest. These are regions that potentially contain diagnostically relevant information. And it also requires evidence collection. And once we have all the evidence, the pathologists need to reason towards a diagnosis, basically putting everything together. So all of these aspects, being multimodal, iterative, and reasoning-driven, make traditional AI models insufficient for capturing how pathologists actually work. That's why we developed PathFinder, an agentic framework designed to mimic this diagnostic reasoning process, from navigating the slides, gathering evidence, and then collaboratively arriving at an interpretable decision. Here's the overview of PathFinder. I will get into the details later, but for an initial assessment, we have our triage agent, which is given the whole site image. It performs a binary classification task for us, whether the case is benign or it is at risk and it needs further evaluation. Then we have the evidence collection phase, where we have our navigation agent and description agent. They collaborate with each other. Navigation agent is responsible to identify critical patches or regions or ROIs, as I mentioned. And the description agent is responsible for describing that critical patch in natural language and passing it back to the navigation agent as a feedback. And this is an iterative process. And once we have collected this evidence, we can pass it to our final agent, which is a diagnosis agent, to reach a diagnosis for us. But before me getting into the pipeline itself, let me quickly go over a few key components that enable this framework. The most important one is the empath dataset. Without this, it wasn't possible to perform this task. So this data set includes 240 H&E whole site images of skin biopsy tissues for the melanoma diagnosis. Melanoma is a type of skin cancer. So originally it was classified into 5 classes, from class 1 being benign to class 5 being the most severe type of melanoma. But in addition to these H&E slides, we have pathologist viewports. So the participating pathologists in this study, they viewed these cases using a digital viewer, and this digital viewer recorded their behavior, basically where they were looking at within this image, the coordinates of those locations, the zoom level, and also the timestamp. So after their diagnosis, we can recreate how they view these images. In addition to that, we also have consensus diagnosis and ROI, which act as our ground truth. But previously, as I mentioned, the ability to locate these ROIs is a critical step in the diagnosis process. So in a previous study, we wanted to automate this ROI localization task by learning from human behavior. So we extract important regions from each pathologist viewing behavior data, and as you can imagine, pathologists viewing behavior differ from each other. So from each one, we are getting different regions that were important in their diagnosis. We aggregate everything into generating a grayscale heat map, which can act as a proxy to important regions. So this image here is a consensus ROI that the board group of our pathologists manually labeled as the region that is diagnostically relevant to the final diagnosis. So as you can see, this image, this heat map, it has a great overlap with this region, which was manually labeled. So these are good proxies for the important regions. We use that heat map to train an autoencoder-based network to learn from the structures of the H&E images to reconstruct those heat maps for us at patch level. And then we stitch everything together to get the whole site image level. And here again, you can see that this region that is lighted up overlaps with the ground truth heat map. So I'll skip the details of this previous work, but if you're interested, you can refer to the paper here. So with that in mind, let's get into the details of our agents. The first one, quickly, let's look at the architecture. We compared this model with some state-of-the-art MIL-based models, and we were outperforming it. If you remember, it's performing a binary classification for us, class 1 versus non-class 1, which is benign. So we were outperforming this one, but let's get into the navigation agent, which is, I believe, the most important part of this pipeline, and it was the most challenging one to come up with. We experimented with different ideas, from imitation learning to RL, but it wasn't possible because our data set was limited, and also the action space is too huge for this task. Even when we talk to our pathologists, they don't know what is the best next action. So it was really hard to simulate that in an RL environment. Then we explored some VLM-based approaches, but again, the model were overfitting. The idea was to ask a LLaVA-based architecture training and ask it, where in the image should I look next based on the evidence that I have collected so far. But it was overfitting, and it was mostly referring to the regions in the center of the image, again, because of the limited size of our data set. So after a few experimentation, this is the final design that we came up with. We were basically building on top of the ROI localization project that I just described, the autoencoder-based system. So we have a unit model. Basically, we provide the downsampled whole site image to it, and we condition it based on some text descriptions that we have collected. And it generates that heat map for us that is a proxy of like which regions are likely informative. And once we have that, we can have a 16 by 16 grid and probabilistically sample one region. So we calculate the average value, average intensity level within each cell. And based on that value, we probabilistically sample these regions. And once we have that, we refer to the high resolution version of this whole site image and analyze it at that high resolution, so we have more details. We're basically going above that autoencoder-based architecture by this text encoder. We're guiding it where to look next based on the visual and textual cues. So the way we trained this navigation agent is that first we needed some paired image and text. So we generated this automatically by using the unit model. We generated patches from these heat maps, and then we use our Quilt-LLaVA or description agent, which I will describe later, to generate descriptions for us. And then we paired these image text pairs, and we mask those regions. Basically, we have one image, let's say this one, for example. This description belongs to this patch, so we mask it, and we also mask that in the heat map side. We repeat this process, and we also paraphrase the descriptions that we have seen previously, and this allows the model to learn the relation between visual regions and textual evidence. Then we have our description agent, which is basically Quilt-LLaVA, the VLM that I introduced earlier. But the original Quilt-LLaVA tends to be quite verbose. It generates longer descriptions, but that's not the type of behavior we're interested here. We want short, concise responses. So that's why we distilled Quilt-LLaVA's responses using GPT-4 to generate concise, like about 20-word long descriptions from Quilt-1M dataset. And then we fine-tuned Quilt-LLaVA with this new distilled data to make it more focused and clinically relevant for our use case. And we also performed a clinical evaluation with 2 of our pathologists. We got descriptions on a small set from GPT-4o, LLaVA and our description agent. And it was done in a double-blind format. We showed these descriptions for pathologists, and they voted which description is better suited for that image that they were looking at. And as you can see here, our description agent performance is on par with GPT-4o, which is significant because it is like the size of this model is very smaller than GPT-4o size. And then finally, we have our diagnosis agent, where we aggregate all the textual evidence that we have collected previously, pass it to a language-only model with a classification head on top to perform the multi-class classification task for us. Given the limited dataset size and also the computational budget that we had, we decided to use a lightweight GPT-2 model for this task, which performed well enough for this setting. So now that we have seen all of these different agents, let's get into the details of how our full pipeline works at the inference phase, specifically this evidence collection phase. Again, we have this whole site image, downsampled whole site image, which we pass to the navigation agent, and it creates a heat map for us. We probabilistically sample a region, get that patch at a high resolution, at 10x resolution, and then we pass it to our description agent, which provides a description in natural language, a short description. So in the next iteration, we want to mask that region that we have already viewed. So we mask that in the next iteration with the background. So we are basically signaling the model to ignore that or treat that as background, not the tissue, and focus on the rest of the tissue. And then we condition that unit model. If you remember, we had a text encoder. We condition that navigation agent based on the text of that region. So we repeat this process. Now we have a new heat map. We select a new patch, generate the description, and in the next round, now we have 2 regions that are masked. Again, we repeat this process multiple times until we have a full trajectory. So you can view a trajectory as one pathologist going over a case, identifying evidence towards a diagnosis. And similar to how it is done in real life in clinical settings where we have multiple pathologists review a case and then do majority voting, we follow the similar approach. We repeated this process multiple times to get multiple trajectories. So once we have multiple trajectories, we concatenate everything and pass it to our diagnosis agent to perform the diagnostic task for us. So for the evaluation, we performed a few experiments. First of all, the human expert performance for this specific task, for the task of melanoma on the test set of MPath dataset, is 65% accurate. Again, this is a very challenging task even for expert human pathologists. So the first set of experiments were the traditional ML models. So a SCATNet is the architecture based on transformer. These two are like, they have some additions to on top of the SCATNet. And then we have some MIL, the state-of-the-art MIL model. We also experimented with replacing the backbone with embeddings from Conch, Uni2H, and Quilt-Net. So the best performing model had a 66% accuracy. Later we wanted to look at the LLM. So without further fine-tuning, are LLMs capable of diagnosis? The original question that I raised earlier, without any further fine-tuning, are they capable of performing this diagnosis task for us? So we experimented with different sets of LLMs, from general ones to more biomedically focused ones. And as you can see the results, they're not even comparable with what we have in the traditional ML pipelines or the human experts. And then we get to the ablation section of our model. Basically, we wanted to experiment with different modules of this pipeline to make sure that every single module or agent is necessary and is actually contributing towards the final diagnosis. So for example, we had an experiment that we removed the triage agent. This one that you can see here, let me get the laser pointer. This one, the no triage agent. Then we experimented with the navigation module. First of all, so the navigation is actually responsible for identifying important regions, right? Important patches. What are the other ways to get those patches? These first three experiments, we are using ABMIL with different backbones, and we get their attention map. And based on those attention map, we extract the top patches. We also had an imitated sampling one where, so we already have the viewing behavior data from pathologists. So we can extract some statistics from them, and then based on those statistics, imitate those behaviors and extract the patches based on that. This is what that imitated sampling is referring to. Then we have our visual-only navigator, which is our navigation agent minus the text encoder or text conditioning. Basically, it is selecting the patches only based on the text, based on the visual data. And finally, we have this exhaustive search where we are not selecting patches. We're basically getting every patch that includes some tissue and throwing everything, all the data, entire tissue at the model. Besides that, we also experimented with the description agent. For example, we replaced it with the LLaVA model. And we also experimented with this text encoder that we had in the navigation agent. We experimented with a clip-based encoder and also a T5-based encoder. So the best performing model was this one. It includes all of our agents. The unit agent text conditioned with a T5-based model, which achieved 74% accuracy, surpassing even human expert, and it was the first time even achieving this number in this task. But despite PathFinder's success and innovative design, it has a few limitations. Currently, our system is limited to skin cancer because the training navigation agent requires pathologist viewing behavior data, which is not yet widely available for other domains. That's why I mentioned that MPath dataset was really critical in designing this pipeline. And additionally, the complexity of the navigation agent's decision-making and occasional hallucinations that we get from the description agent can introduce noise in the system, which affects downstream predictions. These challenges highlight key opportunities for improvements as we move forward, scaling PathFinder to broader diagnostic tasks. So as a conclusion, I introduced Quilt-1M, the largest histopathology image language dataset to date. We got this data from educational videos on YouTube. It was a NeurIPS paper. And following that, we trained Quilt-LLaVA state-of-the-art VLM for histopathology that has both spatial understanding and can perform complex medical reasoning for us. And finally, our recent work, PathFinder, a novel end-to-end multi-agent framework that can mimic pathologists' diagnostic behavior. Here are my amazing co-authors and collaborators who made this work possible. And with that, thank you for listening, and I'd be happy to answer any questions.
Great. Thank you so much, Fatemeh. It was a very insightful presentation and very impactful work. So if anyone has any questions, you can just unmute yourself and you can ask.
I have a quick question. Thank you so much, Fatemeh, for the great talk. I might have missed this part. I'm just wondering, for the YouTube videos that you took some pictures of them. So for that, did you do any sort of pre-processing for the images that you were taking, or did you change the speed, or you did any other sort of analysis to make sure that the quality of the images that you are getting and the resolution is fine enough?
Yeah, that's a great question. It is very important to have high quality images in this pipeline, and we actually ran some analysis to see what are the resolution of these images. I might not remember this like entirely, but I think on average it was like 1,000 pixels by 1,000 pixels, which is very high quality for this domain. But the thing to note is that when we were processing these videos, we were looking at the lowest resolution possible to make everything faster. But can you see my screen here? I think.
No, we cannot.
I think I stopped sharing. Let me. Sorry. Okay. Go back. Yeah, in this pipeline. So yeah, we processed the videos at the lowest resolution possible that YouTube was providing to make everything faster. But when we were actually extracting those, once we identified which frames we were interested in, we got them from the highest resolution possible. And the average was about like 1,000 by 1,000 pixels, which is high resolution enough for these tasks. Anyways, in the downstream performance, they're going to be downsampled to very small, like 284 by 284, or like 384 by 384, something like that for clip, for example. So 1,000 by 1,000 was high quality enough for this data set.
Awesome, sure. Thank you so much.
Yeah, thank you.
Does anyone else have any questions? Okay, in the meantime, I'll just ask a question. So I'm very curious about what's the robustness to ambiguous prompts. Like, since the model is like a conversation assistant, right? So what's its performance when it's confronted with like inherently ambiguous or probably intentionally misleading questions? Like, for example, say the previous patch was normal, and does this next patch of inflammatory cells confirm malignancy, even though the cells actually indicate that it's benign? So just wanted to know, how does the model prioritize its visual evidence over potentially deceptive text?
That's an interesting question. We haven't actually checked for that, but I can imagine that once. So as you can see, let me go back to the slides. Go back to this pipeline. So here, as we move forward, the regions that are being highlighted by the navigation agent are shrinking. So there is a limited set of regions that are informative. And even if we only have, so in the histopathology domain, even if we have a small region that is malignant, we are labeling that whole site image as cancerous or malignant. So even if a single region, so once we repeat this process to get multiple trajectories, and we repeat this process, we are doing probabilistic sampling. So in every iteration, we are looking at different regions of the image. I believe that in the final stage where we are appending all the trajectories together, we have evidence from different regions of the image. So at some point we probably have reviewed regions that contain malignant features. So I'm assuming that it is resulting in a good performance, but we haven't checked. As you said, like if someone intentionally says something misleading, it might generate hallucinations or affect the downstream performance. As I mentioned earlier, it is limited with the ability of our description agent. So once we improve this description agent and have higher quality descriptions, then we are improving the entire pipeline.
Yeah, I think the model should be very spatially grounding. Even though there are any misleading prompts, it should be able to not go along with the plan, but at least the features are well captured. Then in that case, it should be fine.
Yeah, that's a great point. And another thing that I want to note is that clinical evaluation can play an important role here. So, for example, maybe having some pathologists participate in this study and using some feedback from them and applying some RLHF approaches, getting like that clinical feedback into the system can also improve that and is a way to avoid those hallucinations. And actually, I think our group is working on a similar idea to expand this model to include pathologists' feedback into the system.
Okay.
Sorry.
Go ahead.
So is this a reinforcement learning setting where you're training that agent?
Not this one. For this current PathFinder pipeline, we are not doing any RL. But as I mentioned, our group is working on another series of projects which are expanding this work to include RLHF.
So when you're training this agent, you have you have exact data in order to teach the agent what to do.
Can you elaborate what you mean by exact data?
So how do you train the agent to do the right thing?
This really
is it supervised? Is it supervised, or is it something else?
Not entirely. So every agent is trained individually, and then they come together to collaborate towards a final goal. Let me go back to, let me see. So our final diagnosis, yes, it's supervised because we have consensus labels for each case. We know the final diagnosis. But for this navigation agent, we're basically generating these heat maps based on some additional data that we have from the viewing behavior. So it's not really, we are actually generating our ground truth. So it is kind of supervised learning.
Okay, but if you, I'm wondering if you already have ground truth for this, why not a traditional model? Why an agent? Presumably, an agent takes a certain actions in order to accomplish a certain goal. But I'm just wondering why not, if you already have supervised data, why not, for instance, put it into an LLM and then train the LLM to get the right output? What exactly is the agent doing there?
Yeah, that's a good question.
I think I probably haven't understood the structure of the flow of your ideas.
Yeah, and also maybe it's just the terminology of the agent, which we're using to refer to how our pipeline works. It has multiple modules that they interact with each other. But basically, going back to your original question, so the traditional models, like the transformer-based and ML-based ones that only look at the visual content, they're not performing well. They're like the best performing one is 66% or very close to the human expert. And also LLMs, without any further fine tuning, they are not performing well. And I can imagine that even if we train these LLMs for this task, as we can see here, for example, let's see this one, this exhaustive search, right? So this is an LLM that is given all the text content from the entire tissue, right? So basically we get a text description for every single hash that includes a tissue, and we concatenate everything and pass it to the LLM and fine tune it to generate the final diagnosis for us. But as you can see, it is performing 68% accurate. So that's why we were performing these ablations.
Which is still better than human.
Yeah, slightly better than human, but it's still 68% accurate.
Okay.
For a task for a diagnosis is very risky. But yeah, that's the purpose of doing this experiment was to make sure that, as you said, are these agents really necessary? Why not throw everything at an LLM and ask it to perform the diagnosis for us? In addition to that, these LLMs, like if we do that, we are not sure where in the image was important for that diagnosis. Again, we are missing that interpretability part that I mentioned earlier that is really important to pathologists. So when we talk to the pathologists that work with our group, they're always hesitant in using these models because they don't know, they see these models as black boxes. They don't know where the reasoning comes from, why this model is generating this outcome. But with our pipeline, we can actually go back and extract those regions, extract the descriptions associated with this region, and actually tell like why we're reaching at this diagnosis. These are the supporting patches and supporting descriptions or evidence that we collected, and then a pathologist can review those. Instead of the entire case, they can review those evidence that we collected.
Okay, so if I understand correctly, when you say agent, you mean a collection of models such as LLMs that cooperate on smaller tasks.
Yes, and they collaborate with each other. That's what it makes it like an agentic system.
Okay.
Yeah,
Okay,
especially in this evidence collection phase. So the navigation agent's next action is reliable on what we have seen before from description agent and navigation agent. So it is not fixed. At each step, it decides based on the evidence that is collected so far, it decides what action, like where to go next.
Okay. And you teach them how to do that explicitly in a supervised manner?
In a supervised manner, in this slide here, yeah, this is how we train that. So we had to generate image text so that we had to generate image text pairs for this. We used that unit, we generated the heat maps, we sampled patches based on the heat map intensity and used the description agent to generate descriptions for those images. And then this is the training set for our navigation agent, where we mask that region and attach it with the description agent, and then pass these two to the unit model. And this is the supervised label. Basically, the model is generating a heat map and is being compared with this ground truth. And then in the next iteration, where we have two patches, first of all, we are paraphrasing the previous description to introduce variability to the data set. So it's exposed to multiple variations of the data. And then we have multiple descriptions here. We mask those two patches. This is how we generate the data and then use this data in a supervised manner to train this unit model.
Okay, I think somebody else has raised a hand, so.
Yeah, go ahead, Matisa, you can unmute yourself.
Okay. Hi, Fatemeh. Great talk. Enjoyed that. I have a quick question to ask you. If my memory helps, the triage agent is trained as a binary class 1 with a non-class 1 transformer over Quilt-net patch embeddings, and before handing risky WSIs to the downstream agents. Yeah, if my memory helps, yeah. But my main question is that what motivated this stage decomposition instead of a single four-way end-to-end model? And
Yeah,
and I have a
that's
sub-question that I will ask after your.
okay. That's a great question. That's a great observation. Let me go back to this table. So that design actually came after we performed some experiments, and we realized that all of these experiments are performing very poor in class 1. So there are multiple reasons for this. First of all, there is an imbalance in our data set. We have fewer class 1 cases in our data set. And also, this pipeline is hugely reliable on Quilt-1M data set. So Quilt-1M data set is also imbalanced towards challenging cases, because those YouTube videos are actually mostly challenging cases that pathologists come together to describe and also like talk about and reach a diagnosis. So it is heavily balanced towards the more challenging cases. So again, the descriptions that the Quilt-LLaVA generates are mostly, they have mostly seen those challenging cases and malignant cases. So that's why we thought, at least that was our hypothesis, that why it's performing poorly in class 1, which is the easiest label, right? That's why we added this. So originally we had, let me go back. Originally we had these 3 agents: navigation, description, and diagnosis agent. But we added this triage agent to perform this binary task for us. And if it's needed, we can perform the rest of the experiments. And let me also add this. So that's why we had this ablation study of removing no triage agent. We wanted to see if that triage agent is actually contributing to the final number that we were getting, which actually confirmed it.
Got it. So I have a what-if question that I want to add to that. And how does triage misclassification, I mean, especially false negatives, propagate to the overall full class diagnostic accuracy compared to, for example, ABMIL or trans-MIL type baselines that are actually trained directly on all classes?
Can you repeat your question?
That's a fundamental question, but I don't know whether you've mentioned that during your talk or not.
Can you repeat your question?
Yeah, my main question is that, for example, if we want to consider triage misclassification, especially on false negatives, how it could, for example, propagate to the overall four-class diagnostic accuracy via, for example, ABMIL or trans-MIL baselines, because they are trained on directly on all classes. And
yeah, I can see your point. So yeah, it can. The noise can propagate to the final diagnosis. That's for sure. We didn't perform any analysis on that one, but let me see. So if the case was not easy to label as benign, and it needed like further evaluation, so maybe that's the case that we are unsure, or maybe a pathologist is unsure about their diagnosis. So again, in the final stage, we are doing the 4-class classification, and we're hoping that at that stage we are able to capture that, whether it's benign or the rest of the classes. I think that can mitigate this issue, but again, we need to run some experiments to make sure how those misclassified cases are affecting the final diagnosis. That's a great point. Thanks for that.
Yeah, awesome. Many thanks.
I would really appreciate it if I could ask another question.
Yeah, go ahead.
Tashnik Abraham has recently tweeted about a paper that significantly reduces the amount of data required for training a pathology model. And if my understanding is correct, they basically use self-supervised techniques to do embeddings, which understand images, just understanding images, whether something is related to something else or not. And then using those embeddings, presumably they can train a model to understand whether this is cancer or not, something like that. But my understanding might not be correct. But they report very significant reductions of data, like with 12,000 images. They do that. So I'm just wondering whether those kinds of techniques are applicable to the work that you're doing, and whether you have any comments about any possible limitations that they might have for your work.
Okay, I'm not familiar with that work. Could you like share that in the chat if you have a link or something?
Absolutely, yeah.
Yeah, that would be really interesting to see. Yeah, I have to read that paper. Is it a paper or?
If just okay, training state-of-the-art pathology foundation models with orders of magnitude less data. I can just okay. If I'm not mistaken, this is the paper. And I think Tashnik Abraham commented about this, and he has done some further work in this regard with this model, if I'm not mistaken.
Okay. Yeah, thanks for sharing this. I will review this later. But sure, I think there's always room for improvement using techniques, and I think the field is moving towards that way, to use fewer data samples but higher quality data to train more efficient models and pipelines. In our case, the data set that we were working with had only 240 whole site images. And even when we got the patches, we couldn't have like gotten multiple, like millions of patches or like thousands of patches, as you mentioned, in that order. And as I said, like we experimented.
You mean you had only hundreds of images to work with?
Yes, 240 whole site images.
Oh, okay.
Whole site images. Yeah, that is very low in this domain, and that's why we had a lot of limitations on our evaluation side, on our training, especially like designing the navigation agent. So as I mentioned, we had this original idea. It has actually started, so that agentic system actually started with navigation agent as a VLM, so a LLaVA-based architecture, because there were previous studies for using LLaVA for object detection, where you apply a grid on this image and ask the LLaVA model or the VLM what is the patch ID for this specific object. We were following the same idea to provide the evidence that we have collected so far at a specific point, and asking the LLaVA model, like, up to now, based on what you've seen, what is the next patch ID that I should visit? That was the original idea of this agentic system. But again, because of we performed a lot of experiments on this with different designs, but because our data set was very small, it was overfitting. Like, there wasn't any way to get a good result out of this. Most of the patches, the patch ID that VLM was generating, were focused on the center of the image, which showed a clear sign of overfitting. So I think one action that could be taken to scale PathFinder design is we show the potential of this work, of how this viewing behavior data can actually enhance these pipelines. And these days with so this empath data set was collected over 10 years, which was a very long study. But with these days, with the advancements of digital pathology, I think we can get these type of data faster. So it is a motivation for the clinicians to actually acquire this type of data across different types of pathology. So our study was focused on skin cases. Maybe we can expand that to other tissue types and get more data, and then we can train better models here.
You mean even this small amount of data took a long time to collect?
Yes, because it is an older study. It was collected over 10 years, and they had to ship the actual GLASA slides around the United States to the participating pathologists, and then they had to review, they had to send it back. So it took a long time to collect that data. But these days, I think this was done a few years ago, but these days with the advancements and getting like more institutions having access to those scanners and generating their own cases, we can streamline that process and get this kind of data at a higher scale.
Thank you so much for giving this talk.
Yeah, of course. Yeah. Thank you for listening.
We really appreciate it. Thank you.
Yeah. Thank you.
Yeah, thank you so much, Fatemeh. Thank you for patiently answering all the questions. I know it's past an hour. So.